I'm going to assume that you know many of these things. I'm just doing a very quick revision of things that I'm assuming you know. Okay. So, and then we will move on to today's topic, which will be focusing on how to solve problems using these. So first, these are the quantities that we have been using. Displacement, velocity, acceleration are the quantities that we use when an object is moving, either in a parabolic path, straight line, it doesn't matter. We call this translation. When an object moves, generally we call it translation. So suppose I take this ball and this ball was doing this motion, it is still translation. If it was going in a circle, it is still circular translation. But if the ball is rotating, which means you hold it and you start to see that things are moving around something that you are holding in the ball, that would be called rotation. So if I look at this object and I say let me fix this point and this whole thing is rotating like that, then we say that this is fixed axis rotation because the axis is fixed, and that's what we're going to focus on, okay, for now. So when you take fixed axis rotation, this point, which is let's say C, so if this is A, I'll use A to represent axis, C is some point there, and when this point turns around like that, you can see that we can measure this angle theta. And if theta is measured in radians, we usually talk about arc length, and we use the symbol S again for arc length, which is not very good, but people use S for arc length as well as displacement. Displacement is like this, arc length is like that. If you make the angle very small, displacement and arc length will be the same. And this is the radius. And then you know that theta is S by R or L by R. So you are doing a by R whenever we are finding displacement. Because displacement has that by R, because you're going into angle, so we call this angular displacement. So all motion quantities will have a division by R. So divide by R. What do I mean by all motion quantities? Velocity, acceleration, everything is by R. Why is everything by R? Because if S is displacement, velocity is ds by dt. Right? So velocity, if you do by R here, you should also do a by R there. So angular velocity, which is d theta by dt, but theta itself is S by R, so it will be ds by dt by R. So which is ds by dt is V, so you will get V by R. So omega, which is angular velocity, will be V by R. Acceleration, which is a differentiation of V, rate of change of V, is acceleration. But since there was a by R, you have acceleration by R, which will be the angular acceleration. So all motion quantities have a by R. Very simple, just easy to remember. And then equations, like if you look at Galileo's equations for uniform accelerated motion, 3 equations, V equals U plus AT, S is equal to UT plus half AT square and so on. Then V by R is omega. U by R is initial angular velocity omega naught. A by R is alpha. So omega is omega naught plus alpha t. You probably already know this. I'm assuming you know this. I'm just doing a revision. Okay. Similarly, S is equal to UT plus half AT square. Divide everything by R. S by R theta. U by R omega naught. T does not change. Time is the same. Okay. So this is omega naught t. So theta is omega naught t plus A by R, which will give me alpha. So alpha t square by 2, half alpha t square. 2as is u square, v square minus u square, divide by r square, because you need to divide by r, divide by r square. So 2a by r will give me alpha, s by r will give me theta, so 2 alpha theta is omega square minus omega naught square. So instead of using a new variable, we just simply use omega naught to say initial velocity, angular velocity. Now the main point I want you to remember is all motion quantities have a by r, division by r. Why do they have a division by r? Because theta has a division by r. So everything else, because everything else is derived from s, everything else is derived from theta, s for this and theta for that. So because theta has a by r, omega has a by r, v has a by r, equations have a by r, everything has a by r. And that's very useful and important to keep in mind. Now let us look at the next point in rotation. And this brings us to the idea of torque. You probably already know that if I'm trying to push, it is easy to push it here than to push it here to make it turn. Which is why if you take a door, all the door handles are kept at that end. No? If you try to push a door from here, you will find that you have to push it really hard, very hard to turn the door. It is very easy to turn the door by pushing it on that end. So always, that is because the turning effect of force is R into F. So F, which is the force in linear terms, basically becomes R times F. We need to add a few extra elements to it and we call it R cross F, because it is not just the fact that the force acts here, the force could act like this, passing through the axis, in which case it won't make anything turn. Like you can't, like suppose, imagine that this was a door and I try to push the door like this, it won't help. I need to pull the door this way or push the door that way. So you need to do it perpendicular to this line. So only the perpendicular component contributes. So we write F perpendicular into R, or it turns out that you can equivalently write it as R perpendicular times F. I have done many of these things earlier for some of you. So, but I am going to focus on this idea. Okay. So, F becomes torque. So, instead of force, we are going to deal with torque. Torque has an into R, R cross F. You have to be a bit more careful about it, saying R perpendicular times F or R into F perpendicular. But as of now, let us just focus on the fact that torque has an into R. But you see, force into time, what does it do? Force into time changes momentum, correct? Force into time is change in momentum. So, force into time changes momentum. Momentum and force in some sense are very similar quantities that way, except for the fact that there is a time, right? So, if force is going to become angular force, we have a new name for it called torque, which means you are multiplying by R. For momentum also you must, because if I multiply by R here, I must multiply by R there. R cross F, R cross P. So angular momentum should be defined as R cross P. Angular momentum is a different form of momentum. It is not the same as momentum. It's not, I shouldn't even say different form. It is different from momentum. Torque is different from force. It's an angular quantity. You cannot say theta and S are the same. It is a similar but different quantity. Angular velocity is not velocity. You cannot add angular velocity to velocity. You cannot add torque to force. You can add 2-3 forces together, but you cannot add torque to force. You cannot add angular momentum to momentum. Okay. So for all force and momentum quantities, multiply by R. Very vague. I'm just kind of giving it as a big picture, this thing. Now if you notice, this is actually the important part. So I want you to understand this so that then we can go ahead and start looking at actual questions. If all motion quantities you divide by R and all force and momentum quantities we multiply by R, mass is defined. I mean, today we use force is defined by m into A, but long time ago when actually mass was defined by Newton, mass is defined as force by A. By the way, even you, when you look at what is your weight is actually force. How do you know your mass? Suppose I tell you that you are 80 kg, that is mass. How does anybody know that you are 80 kg? Because you go and stand on the weighing machine, right? And when you stand on the weighing machine, actually what you are measuring is weight, which is actually something like 800 newtons. And then you divide by 10, G I'm assuming is 10, okay, or 9.8. The weighing machine shows 80 because it's calibrated to divide by 10. Similarly, that's what we are doing here. You take a mass. How will you find the mass of an object? Force divided by acceleration. If I did the same thing in angular terms, I should do torque by alpha. But the problem is torque was what? Multiplied by R. So torque would have been R times F. Alpha would have been division by R. So this would have been A by R. So you see that this R goes up. And so this gives me R square times F by A. F by A would have been mass. So that's why I get R square times M. Now this quantity we call moment of inertia. I am hoping you have studied it. Probably you have just learnt it as a definition saying I is equal to sigma mr square like that. But why mr square? Why can't it just be sigma m? Why can't it just be mr? If torque is all multiplied by R, force is multiplied by R, momentum is multiplied by R, why is mass alone multiplied by R square? Because mass, equivalent of mass, is torque by alpha. Alpha has a by R, torque has an into R. So that means you are doing an into R and a by R in the denominator, which is actually like into R square. And that's why you get mr square. Anyway, so all mass quantities, well, luckily, there's only one mass quantity. So there's only one moment of inertia, luckily, that you need to calculate. Force and momentum into R, mass into R square. All other motion quantities by R. So it's not complicated. This is useful to just keep in mind. There may be small changes that we need to do when we get to the case of non-fixed axis, moving axis rotation, which we won't look at right now. But I'm going to give you the basic laws for fixed axis. F equals ma, Newton's second law, becomes Newton's second law of rotation, which is torque about an axis of rotation. Since we are talking about fixed axis, we are only talking about that particular axis. I'm not using any other axis. Okay, so if a body is rotating about an axis, so for example, if I take this guy, and this fellow is rotating about this axis like that, right? So this is the axis of rotation. It's a fixed axis. In which case you will take torque about this axis. It's force, you don't have to worry, you take inertial frame and you just say force. Whereas here we need to take torque about a fixed axis is I times I about that axis, same axis, times alpha. Okay? So tau equals I alpha becomes the equivalent of F equals ma. Because force became torque, A became alpha, M became I. P equals mv. What is that? Momentum is equal to mass into velocity. All these are vector quantities. So are these. I is not a vector quantity. Mass is not a vector quantity. Alpha is a vector quantity. Momentum is a vector quantity. Mass is not. Velocity is. Angular momentum, I know I have defined angular momentum as r cross p, but you will also find when an object is rotating, angular momentum is I times omega. Direction of angular momentum is the same as direction of omega. Now please remember, this is not valid very strictly. You have to think very hard about whether you can apply it. It is valid for fixed axis rotation. It is valid about the axis. It is not valid when an object is moving, translating and rotating. For example, if I threw this, you have to be very careful about whether it's applicable. Because there isn't a fixed axis in this question. Right? You can talk about the axis through center of mass and you can say this fellow is going up and down and turning. But that's not fixed axis problem. We'll study that separately. For fixed axis, if this is the axis, that is the question. Well, I'm turning it around, but I'm hoping you understand what I'm saying. Right? So for fixed axis questions, this is valid. It doesn't require it to be constant alpha. It could be fixed axis and it could have varying alpha. It can change. Everything else can change, but the axis cannot change. Okay? Now if you notice, F is a new quantity, not new quantity, old quantity. Tau is a new quantity, a different quantity. Torque is a different quantity. Momentum, angular momentum, different quantity. But when you come to kinetic energy, this kinetic energy is half mv square. What should be the rotational case? Half, instead of mi, instead of v, omega, half I, omega square. But there is something very important to note. Notice something. This is a new symbol compared to that. This is a new symbol compared to that. Why is this the same symbol? Because it is the same quantity. It is not the same symbol because it's by mistake somebody decided. It is not rotational kinetic energy. You might have learnt it many times that it is rotational kinetic energy as if this is a new form of kinetic energy. It is not. It is the same old kinetic energy, just that we are calculating it differently. Okay? So, for example, if I took an object and say this is my axis, and if you look at a point there, let's call this point mass mi. If I look at this length, let's call it radius ri. It has a velocity like this, vi. Now everything is changing. Ri, vi, everything is changing. But if I call this ri and this fellow had an omega, the only thing that is the same for this particle and that particle are different. So this will be rj, mj. Okay, velocity vj. But what is omega? Same omega. So this fellow has the same omega, that fellow has the same omega. So if I write vi, I'll write it as ri omega. If I write vj, it is rj, not omega j, just omega. So this particle's kinetic energy, regular usual kinetic energy, is half mi vi square. This is the actual standard kinetic energy. But this must be equal to half mi ri square omega square. Because ri omega is v. Fixed axis rotation. This is the axis. Now if I add up all the kinetic energy for this fellow, this fellow, this fellow, this fellow, this fellow, this fellow, this fellow. It is the total kinetic energy. This is the kinetic energy of the body. It's not a new quantity. This is a new quantity. R cross P is a new quantity. R cross F is a new quantity. You study it only for rotation. This is not the new quantity. This is actually the old kinetic energy. Now the old kinetic energy is sigma half mv square. But that means I must do a sigma here. But half is common, omega square is common, and this guy here is called I. So therefore we find that kinetic energy is half I about A omega square, because that quantity is defined. So if I took mi ri square plus mj rj square, m1 r1 square, m2 r2 square and add it up, that is I about A. So kinetic energy is half I about A omega square. Now sometimes you might learn that you must also add plus half m center of mass velocity square, etc. Don't do that. For fixed axis, if you use the formula I about the axis, there is no center of mass velocity, etc., etc. This is the full kinetic energy. Over, done. Okay. There is a formula which will say half I center of mass square, right? Omega square, I center of mass omega square plus half mv square. We will come back to that formula. That formula is just a formula that we will use as an alternative to this sometimes. Okay. Now that formula, the half I center of mass omega square doesn't represent the full kinetic energy. Okay, this represents the entire kinetic energy, because you see that I've just derived it straight. All it has done is this. It is not different from this, and that is very important to understand. Why? Because rotational kinetic energy can become potential energy, because it's the same form. Just like if I took the ball and I threw this ball up, kinetic energy became potential energy. Potential energy becomes kinetic energy. How do you get electricity at home? You have water coming down, which is potential energy, falls down and makes rotational kinetic energy, turbine, rotational kinetic energy. And rotational kinetic energy is becoming electrical energy. And that comes and rotates your fan here, right? So similarly, if you are looking at motion of a car, how does the car get kinetic energy? Because first the car's wheels get rotational kinetic energy. Rotational kinetic energy can become the regular linear kinetic energy, because they are the same thing. But angular momentum cannot become momentum. If this object has angular momentum, if it's making it rotate, angular momentum will not make the object move forward. Okay, a rotating object will keep rotating. It can make another object rotate, but it cannot get linear velocity. I hope that part is clear. Different things, same thing. It's useful to keep in mind. Okay, now we know that force into time changes the momentum of a system. The equivalent of that is torque into time changes the angular momentum of a system. And I'm hoping you all know how to do things like find moment of inertia for a disk. So what is the moment of inertia for a disk? If I took a disk like this, moment of inertia about an axis. Now every time you talk about moment of inertia, you should know about what. So I'll just simplify matters today. We have done later, maybe we can spend some time on how to calculate moment of inertia. But if you look at this, if it's rotating like this, then we are going to look at moment of inertia for a disk, uniform disk is half times mr square. So I want you to use that to do this very simple question. So I will give you the question here, okay? Net external force into time is the change in momentum of the system. So this is final momentum minus initial momentum. Torque into time changes the angular momentum, L final minus L initial. And what is angular momentum? Angular momentum is I omega for fixed axis, only for fixed axis. So if I take this and I tell you force is 0, suppose net external force was 0. What does that tell you about the change in momentum of the system? 0. Right? Change in momentum of the system is 0 means momentum is conserved. Now please remember, if it was a single particle, this is not a big deal. Why? Because you are saying mass into velocity is constant, which means velocity is constant. But did you already know Newton's first law? What is Newton's first law? If there is no force, no external force, or if the net force is 0, object moves with constant velocity. That is not what this is saying. That is not what this is saying. This is for a system. This is saying if I had 2 objects, 5 objects, 20 objects, they are colliding and doing all sorts of things, there is a spring. So you have a block and a spring in space or even on a frictionless surface, and these fellows are going this way, that way, they're coming, right? So they're doing this as they're moving. What this is saying is, right now this guy may have 10 meters per second and that may have 20 meters per second and some mass m1 and m2. After some time, this guy is much longer like that, and this guy has a velocity this way and that guy has a velocity that way. But if you take the total momentum of the system and take the total momentum of this system, you will find that this and this same system, right? They both have the exact same momentum. The velocities individually are changing. So it is much more than Newton's first law. Actually, this statement comes from Newton's first law and Newton's second law. Oh, sorry, Newton's third law. Okay? Because Newton's third law, in fact, actually all 3 laws in some sense, but Newton's third law tells you that the internal forces cancel out. That's why only external force produces change in momentum. Now, if you take the same idea for torque, this says that if torque, external torque is 0, there's no external torque, then angular momentum is conserved, which means angular momentum final must be equal to angular momentum initial, which means I1 omega 1 plus I2 omega 2 must be I1 omega 1 dash plus I2 omega 2 dash. Dash is one final values of these fellows. Assuming that they are moving with the same axis, we're bringing them together and so on. Let us do one question and then we will start to look at other kinds of questions soon. Okay. So first let us start with a very simple question. What I have here is a disk. Now if you take this disk, let us assume that this disk was rotating like this, like that. Okay. So if I say it's rotating like this, usually we like to point out angular velocity is pointing upwards. So I'm going to say that this fellow angular velocity omega 1 is 2 radians per second. The disk has a radius r1, let us say 2 meters, and it has a mass 1, which I'm going to say is, let us say 2 kilograms. And right along this axis way below, if you come down like that, here I have a bigger disk. So I should draw a proper disk here. It also has the same axis. Assume that this is also symmetric. Okay? So I'm trying to make a 3-dimensional effect, so it's not very clear. But if you take this radius R2, let us say is 3 meters. Mass M2 is 4 kg. And this guy is rotating in this direction. It is rotating in this direction. So I'm going to draw it like that. Is the same direction as that? No, that is rotating like this. This fellow is rotating in the opposite direction. Okay. So this guy's rotation, let us say, is 5 radians per second. Remember, if that direction is positive, this direction will be negative. Okay. So what I'm doing now is there are these 2 disks. So there is one disk like this, there is a second disk. I'm bringing the second disk and the first disk and pressing them down, or I'm just dropping it, okay, whichever way. So once these 2 disks come together, there is a lot of friction between them. So there will be some amount of rubbing. There will be a loss of kinetic energy because friction will do work. But there will be no change in, there will be no external torque. Why no external torque? Why no external torque? Because when I bring this fellow down, there is friction because, so if I think about one surface and the other surface, there is friction due to this fellow there and friction due to this fellow there. But about this axis, both frictions are equal, action reaction. They are in opposite direction and therefore their torque is 0. External torque is 0. So in this case, external torque is 0. So when you press them together after some time, it's like a collision problem where they are sticking. Find final angular velocity of the two discs. Okay, I'm going to give you 2-3 minutes to do it. Come on, quickly finish it. Enter the answer in that box that will come up. So let us look at the solution quickly, because this is not the main thing I'm going to focus on today. Okay, I'm going to focus on problems that look like this, where this guy is going pulling, that fellow is pulling, how much will it turn, all of those questions. We'll come to that in a minute. Before that, let us solve this problem. Now remember, this is not a rigid body, these are two different rigid bodies. Two uniform discs are basically coming together, they are basically sticking together. After they stick, they'll become one rigid body. So the axis for each one, in some sense they are different axes, right? Each one has a separate axis. Just that these two axes are the same line. So we call them coaxial discs. Coaxial basically means same axis. Now let us start with a very simple case. I am going to call this the positive direction. You know that angular momentum, like linear momentum is mass into velocity. Angular momentum, what is the equivalent of mass? I, moment of inertia. Velocity is angular velocity, omega. But it is a vector in the omega direction. Now, if you look at this, you know that omega, use the right hand thumb rule. You turn it this way, the thumb points upwards. So this fellow is turning this way, thumb is pointing upwards. So this omega 1 is pointing like that. Whereas if you take this guy, this fellow is turning this way, opposite direction. Look at that. So opposite direction, my thumb points downwards. And I have taken up as positive, so this is plus 2, whereas this fellow is minus 5 radians per second, that is omega. Let us do this. What is momentum, angular momentum 1? So before that we need to calculate moment of inertia for this guy. So this is 1, right? Moment of inertia half m1 r1 square, because it is an axis passing through its center, it is just rotating, it's like a disc. So you know that it is half into its mass, which is 2, radius, which is 2 square, so that is 4, and so this gives me 4. SI units, kilogram meter square, I won't write the units, I'll just write it as 4, I'll only use SI units. What is the moment of inertia for the second fellow, for this one? It doesn't matter how it is rotating, but it's important that the axis was this way, because then you are talking about a disc like this. Let us think about this carefully. If I take a disc, and if I say that this disc was rotating about, let us say, let me first push this fellow inside. Okay, if it was rotating like this axis, answer is mr square by 2. But it is also possible that this was rotating about this disc, about this axis. That is also passing through the center, but it is not mr square by 2, it is mr square by 4. You might have learnt it with the parallel axis theorem. This axis, the answer is the same as that axis, and you know this axis plus that axis gives me the answer for this axis, that is called perpendicular axis theorem. So sorry, not parallel, in this case you will use perpendicular axis theorem. So this I plus this I gives me this I. This I know is mr square by 2, so each of those other axes, the answer turns out to be mr square by 4. But here we are talking about this axis. So this guy is rotating like this. So here, let us take this case. This disc is rotating like that, and the disc on top is rotating in the opposite direction. This fellow is rotating like this, that fellow is rotating like that. And then you are placing that disc on top of this. So therefore, both these discs push each other, exert torques on each other, and then finally come to a point where they are moving together. So that is the final state. So if you draw the final state, in the final state, this is how it's going to look. This disc and that disc, they are moving together. Now they may be moving this way or that way. I'm going to assume that they are moving like this, and I'm going to call that omega. If it turns out omega was negative, that means they are not rotating in this direction, they are rotating in the opposite direction. That's all. So let us calculate I2. So moment of inertia for this fellow, Whether it is rotating like this or rotating like that, it doesn't matter. It is the same moment of inertia. Half its mass 4 into radius square 9, 3 square 9. Never say half mr square, because many times in the problem you may actually have 2r instead of r. So it's a good idea to say half into mass into radius square. So if I did this, this is going to cancel out 2, 2 into 8, 2 into 9, 18. So I2 is 18, I1 is 4. What is the momentum, angular momentum 1? I1 omega 1. How much is that? That is 4 times 2. 4 into 2, 8. Plus or minus? Well, it is pointing upwards, so it is plus. So this fellow is plus 8. If you want units, you can say m kilogram meter square into radians per second. I am not writing the units, it's SI units. Momentum of this fellow, angular momentum, not momentum, momentum, rotational momentum of this fellow. Well, this guy is rotating in this direction. It is this way. If I do it this way, it is not, I should use my finger to say this way. Therefore, it is pointing downwards. So I will write minus 5 is omega 2. Okay, so omega 2 is minus 5. So if I substitute that here, I2 omega 2, I2 is 18 into minus 5. Well, that is minus 90. Notice it is minus 90. So if I find the total angular momentum. Angular momentum initial, this is the total angular momentum, is 8 minus 90. How much is 8 minus 90? That is going to give me minus 82. This must be equal to the total angular momentum final. This must be angular momentum final. But if you take the angular momentum final, you have this disk and that disk. It is not a hollow, it is not like a disk where you have cut this part out. That fellow will be called, what is that kind of a thing called? Annular disk. This is not an annular disk. It is a full disk, and on this full disk I have placed one more full disk. So it is just simply moment of inertia just simply adds up. So what is the moment of inertia? I1 plus I2. How much is that? Or you can write I1 omega plus I2 omega, which is I1 plus I2 omega. Moment of inertia just simply add. No minus and plus sign for addition of this. So it is just simply plus both of these. So 18 plus 4. How much is that? 22. 4 plus 18, 22. SI units again. So final momentum, angular momentum is total moment of inertia times the final omega. And so if I divide the two, I get omega final is minus 82 by 22. If I divide out by 2, I will get minus 41 by 11. For this I will write units. SI units for omega. What is it? Everything was done in SI units, SI units, SI units. So the answer is also SI units. So it is just simply radians per second. Okay? So that means I know that the final omega is minus 41 by 11 radians per second. Well, if you did your calculation, this may come out to how much? About close to 4. So minus 4. What does that mean, minus 4? It means this whole thing is not rotating in this direction. It is rotating in this direction. It is rotating like this. Because you see, this guy had a very large moment of inertia and it also had a very large angular velocity. So it had a large angular momentum in this direction. This had a small angular momentum in that direction. Notice I am subtracting and I am not just adding. Okay, you have to add angular momentum. When you say L1 plus L2 is L final, these are vectors, which means they come with sign. You should know that this fellow is positive, this fellow is negative, and the total answer turns out to be negative, which means this is not rotating like this, it is rotating like this in the opposite direction. So I hope this is clear. Just can you please check whether everybody understood this solution?